All right, everybody. So today we're going to go over inductors and capacitors. I know for the inductors portion, that's probably a review for a lot of people over things you've already done, but I want to go back through it again. So inductors, we have two symbols we work with most with me. Is this type of symbol for an inductor with an air core, this type of symbol, inductor with an iron core. You have XL equals 2 pi FL, where the lowercase f represents frequency. Frequency is 60 hertz unless otherwise stated in any question. So if you get a circuit and it doesn't have the hertz designated, it's 60 hertz because we're working in the United States. Now, series for the inductor, L1 plus L2 plus L3 will give you L total. XLT, the total of XL, will equal XL1 plus XL2 plus XL3. And you will use the inductive reactance formula using the inductance to find those locations, to find the values in these areas. And unit measurement for XL is ohms. So XL is in ohms, L is in henries. When you're working, that's when you're working a series circuit, they add. When you work a parallel circuit, it's just like resistance in a resistive circuit. Use the inverse formula or the reciprocal formula, whichever you want to call it, whichever somebody's ever taught you as. That's fine. You still do the same functions. Now, E equals I times XL in a purely inductive circuit or at each inductor. So if you have XL and you have I is current, you have current and inductive capacitance at inductive reactance at the inductor, then you can find the voltage. Now, we're going to roll over to capacitors. Capacitors are slightly different. The formula to find capacitive reactance is 1 over 2 pi FC, F being frequency again. And once again, frequency is 60 hertz unless otherwise stated. And C is your capacitance, and that's measured in farads, the capital F. In series, you'll use the inverse or reciprocal formula to find capacitance total or capacitive reactance total. Right here, you'll use the capacitive reactance formula to find capacitive reactance if you have capacitance given at any points in the circuit. So if you have the capacitance like 4 farads here, 2 farads here, and 3 farads here, you can go through and calculate and find all the capacitive reactance. And then you can add them all up or do the formula, kick out your answer for capacitance, kick out your answer for capacitive reactance, and then you can run it through the formula again to make sure you're right. Cross-check. E equals I times XC in a purely capacitive circuit or at a specific location, like on a branch that's capacitive. When you get to parallel, capacitance total equals C1 plus C2 plus C3. It's just the opposite of way resistive circuits work and inductive circuits work. XCT does the same thing. Capacitive reactance does the exact same thing mathematically. Now, non-polarized and polarized capacitors. We're going to be working with non-polarized in the class. This makes it easier on the math for us. And that should cover how to solve these. Now, if it's a series circuit, we're still using Kirchhoff's law. Kirchhoff's law in a series circuit, current is constant. In a parallel circuit, it's Kirchhoff's voltage law. Voltage is constant. So you have to go back and use other information from that we have learned previously, or you have learned previously, not necessarily with me, and bring that forward and use it. And this will cover inductors and capacitors in series and parallel. We will be going into inductive resistive circuits and capacitive resistive circuits, and then the combination of all three eventually. Thank you.